Welcome back. This video is picking up where the last video left off. We learned about random samples, we learned about what random means, and we learned about why we take random samples. Because it gives us our best shot at getting a sample with a mean that matches the true population mean. So the video also mentioned that we do this because we're usually interested in a pretty big population and we don't have the means to go collect data from every single person in that population. Maybe you want to survey the whole country, and that's not at all uncommon in sociology. I want to know what Americans think about X. So we don't have the time or the money to usually do that. We often can't even identify every single person in the country. So we have these huge populations that we're interested in, and we can draw samples to understand something about them. And there are a couple of rules. One, as I've already mentioned, taking a random sample is best. It gives us our best shot at our mean of that sample matching the true population mean, or the actual population mean. So that's the first rule. The second rule is the bigger the sample, the better. And the third rule is sort of that when we take enough samples over time, it will sort of regress toward the actual population mean. If we take a sample of just size, here we have a sample of just two people. And we see that the mean of that is 48.5. It's different from the actual population mean by 6.8. And here's another sample that we just took at random, and the mean there is 30.5, so it's quite a bit off. The actual mean here of 41.7, it's off by 11.2. Here's another sample of size 2, and it's off by even more. It's off by 26.8. So the point is that random samples give us a good guess, but tiny random samples don't always give us a very good guess at what the true population mean is. Or in statistical terms, they're not very unbiased estimators. They don't give us a good estimate of the actual population. So if we take larger samples, here we're adding 3 to each sample. And like magic, there's so much stats magic happening in this class, but like magic, these means of the sample, so this is the mean of sample 1, sample 2, sample 3, and they're pretty close to the population mean. They're off by between 3 and 7.5, but that's much better than what we were dealing with here when we were off by up to 26. So having a larger sample, and it makes sense to most students, I find, that taking more people out of that population gives us a better shot at getting a mean that matches that actual population mean. And it seems to make sense. But you can see that what we're doing here now is what we call a mean of means, which we actually don't call that because it's so awkward to say mean of means, mean of means, mean of means. So instead of saying mean of means, we say the grand mean. So this is the grand mean. It's literally a mean of these 3 means, right? So here we've done this with the average distance, but what we can do is average our 3 sample means, and this is a mean of means, okay? This is a true bona fide mean of means right here. So this mean of means is 41.2, and look, I love this. This is why I love statistics. Because when we take samples, we take the means of those samples, and we take the average of those means, we take the grand mean, we take the mean of means, those are all the same thing. Look at how close it is to the actual population mean. And that's the magic about sampling and theoretical sampling distributions. In practice, if you're taking a sample of 1,000, you're doing it because you need to save time and money. You can't sample the whole population. But if you take that sample of 1,000 and you do it 10 times or even 3 times, it's costing you too much money. You can't do it. So we don't do this in practice. And that's one thing I find that students can get caught up on. That. How does this really work in real life? How would you do this? You don't do this. This is theoretical, but we do it in order to show what we call the central limit theorem. That when we take a sample and we take the mean of it, if we were to do that over, hypothetically, theoretically, if we were to do that over and over and over again, we would see that the mean, or the mean of means especially, will get better and better and better. And by better, I mean closer to the actual population mean. So here's a great tool, and I posted this on Blackboard, online stat book. It's a sampling distribution simulator, and it will show you this. And it's teaching you the central limit theorem. So we like this nice distribution, this normal bell curve shape in our population. And that's what we need to have that kind of shape to be able to do z-scores and things like that, like we've been doing. If not, the inferential statistics that you're about to learn don't work. So we need that normal distribution, that bell curve shape. But what if we don't have that bell curve shape? What if we have this terrible thing, or skew, or something even more hideous? Maybe it's almost even some kind of wacky U shape, right? Or something like this. This is just a terrible distribution. We can do nothing with this in terms of inferential statistics. But the point is, this simulator lets you take a sample of some size. Let's take a sample of size 2, like we did in the Excel sheet. And let's do that 5 times. This is how many times we take the sample. So that's what we have. It looks pretty wonky too. But if we take 10,000, it's getting more normal. And if we take 100,000, not much. Incidentally, we see that with a sample size here, we tend to not, we see sort of a diminishing return as that sample size gets bigger. Around 30, we start to get a pretty good sample usually. And by good we mean it's a good estimator. The mean of that sample is a good estimator of the actual population mean. As we go up to 100, it gets even better. And up to 300, fine-tunes even a little bit more. But after that, you're getting really tiny changes. So we love samples of around 100 to 300 because it's sort of the small sample that gives us good quality. And that's sort of a side note, but a very important one as you go on to do statistics. But let's bump this sample size, these sample sizes, we're doing multiple samples, from 2 to 25. Get us a better sample. Remember, bigger samples are better. Bigger is better in this case. So here we have samples of size 25. We take 5 of them, and look at that. It's not looking too bad. 10,000, it's just picture perfect. So the bigger the sample, the more you have the central limit theorem on your side. And that's why you read in the book about something called the law of large numbers. And the central limit theorem and the law of large numbers are siblings, maybe even twins. Because the point is, when we get bigger and bigger samples, or we take more and more samples of some size, we get better and better distributions, at least in terms of being normally distributed, which is that beautiful bell curve shape that we can use to compute z-scores and do other inferential statistics. So hopefully that makes the point there a little bit. And like I say, this is online. You can go into the weekly materials and find this and experiment with this and hopefully get the idea of what's happening there if it's still a little unclear in your mind. But what we show here is this same idea that when we take a sample of some size, we get, the bigger it is, the better it is in the first place. From our smaller sample of 2 to our larger sample of 5, any given sample seems to have a better, or at least has a better likelihood of having a closer mean to the actual population mean. But when we average that, good things are happening for us. So let's see this in practice a little bit. Here's a data set of 10,000 teacher salaries. It just keeps going and going and going and going and going and going. And I simulated this. It didn't come from real data, but let's pretend we have this population, that on this side, this is our population of 10,000 teachers. And we want to know about every single one of them. But we don't have the money to do a sample this big. We don't have the time. We don't have the staff. So we can take a sample of size 3. This is a random sample, and I did set up a simulator here in Excel, similar to the simulator that we were just using. So samples drawn randomly from the large population of 10,000. And this is just a sample of size 3, just a tiny sample. But when we average that out, we get our sample mean, and it's 48,000. It's not too bad at all, considering that this is a sample of size 3. And if I run a simulator, I can do repeated samples. So you see this sort of ranges, if you focus on this number here, it ranges from 48 to 68, something like that. And these are repeated samples. So here's a sample of size 3. This is the mean of it. Here's another sample of size 3. There's the mean. Here's another one. There's the mean. So you can see that they're kind of ballpark, but they're not great. So let's bump up to a sample of 30. We have enough money that we can survey 30 people. So here's a mean, 55. It's pretty close, really. 55.9, just about 56. 57, that's pretty close. 59. You can see there's not as much variation. We're somewhere between, I don't know, 54 and 60, 53 and 58 maybe, something like that. So it's closer. We're not varying clear up. Here's clear up to 73 on the sample of 3. So our samples of 30 are better, but when we take repeated samples, they're a lot tighter. So it's that central limit theorem again. We're getting that tighter, we're getting a normal distribution, but we're getting a tighter distribution. It's not spread out, so it's sort of easier to work with. So here we have a sample of size 100, and again we can take repeated samples. And look, it's just varying between 54 to 57, or there was a 59, but it's very rare. Mostly 55 to 57 or 8. So it's getting even better. And this is what I mentioned earlier, that when we have a sample of size 30, it starts to get pretty close. We would really take most of these, 54 to 59. This gets even better. Most of these samples come in 55 to 58. Looks really good. We can go up to 300 and get even better samples here. We're between 55,600 and 57,200. We're just really tight. And you can see that when we go up from 300 to 1,000, we don't get that much more benefit. So, again, this magical number sort of 30 is kind of our minimum, and 100 to 300 is really where we like our samples to be. So, one more note in closing to go along with the simulator, the website. Here I've taken each of these. So this is a sample of size 3, and I wrote down the numbers from 3 of these simulated samples, and then I averaged them. Then I did that for the sample of size 30. Here, now these are means, okay, sample means. So this was one sample mean of the sample of size 30. Here was another sample mean of sample of size 30, and another. This is for a sample of size 100. There's 3 different means. 300, there are 3 different means, and so on. So up here at the top, this is averaging those. This is the grand mean, again, or the mean of means. So what you can see is that the same thing we saw in this other simulator on the website, but in a little different format. The point is that when we average our sample means, we take these grand means, they're pretty close. We're dealing between 66.6 and, or really here's a 55.2 and 58.0. So we're right around this population, this actual population mean. So the bottom line is, this is one of the most exciting things in statistics. When we take samples, if we take a random sample, and if we take a bigger sample, and we don't need a huge sample, 30 is okay, 100 to 300 is usually great, and it does depend on a few other things, but usually 100 to 300 is a pretty great sample. And with that sample of 100 to 300, because of the central limit theorem and the law of large numbers, when we have that sample of size 100 to 300, we are in business usually. We're usually getting a pretty good sample, and we're pretty confident, and this is, we'll talk more about this later, but we're pretty confident that we have a decent estimate of the true population mean. I hope this helps clarify this a little bit, and good luck with the lesson modules this week.